Acid-base salts, looking at solvolysis and the salts of acids and bases. The solvolysis is a process by which a substance will react with the solvent it dissolves in. If that solvent is water, it's called hydrolysis. Some solvolysis processes involve hydronium and hydroxide, so are involved with acids and bases. For example, the conjugate base of an acid can react with water to reform the acid and hydroxide. Usually, this kind of solution is basic, so we form excess hydroxide. Adding the salt will upset the equilibrium. The reaction then moves to the right. Conjugate base of a strong acid will be a weak base. The conjugate base of a weak acid, though, will be a stronger base. So looking at something like nitric acid forms the nitrate ion, which is a weak base and doesn't appreciably go back in the ionization towards the left-hand side. Acetic acid, though, on the other hand, will form acetate. Acetate is a fairly strong base, which can react backwards to form the acetic acid again. Looking at dilute solutions of these salts, dilute strong acids and bases will ionize completely. Dilute weak acids and bases will come to an equilibrium. We can explore the solvolysis of salts that form from acids and bases in terms of strong acids and weak acids, strong bases, and weak bases. A salt of a strong base in a strong acid is one possibility. A salt of a strong base in a weak acid is a second possibility. Salt of a weak base in a strong acid is a third, and salt of a weak base and a weak acid is a fourth. Now, salt of a strong base in a strong acid is formed from two solutions which are completely ionizing and will always be neutral in pH. The cation of a base and the anion of an acid form a salt. If I dissolve a salt of a strong acid and strong base like NaCl, it involves two different reactions. The first reaction is the dissolution, forming Na plus and Cl minus. The second is the autoionization of water. In theory, Cl minus can react with H3O plus to form HCl. However, because that conjugate base, Cl minus, is so weak, very, very little ionization actually occurs. So the concentration of H3O plus remains relatively constant at 1 times 10 to the minus 7. This doesn't upset the Kw one way or the other, so concentration of both H3O plus and concentration of OH minus remain the same, leaving the solution at a pH of 7 or neutral. Looking at the salt of a strong base in a weak acid, however, this salt will always be a basic salt. A minus will react with H2O and H3O plus, making excess OH minus. If I look at this process, there are three reactions. NaCH3COO will ionize to form acetate and sodium. Water will autoionize to form hydronium and hydroxide, and that acetate can react with hydronium to form acetic acid in water. This consumes the hydronium faster than it consumes the hydroxide, which makes the solution basic overall. Acetate will then form acetic acid in solution. If I look at the overall process, acetate plus water forms acetic acid and hydroxide. The equilibrium constant for this process is referred to as a hydrolysis constant, or Kb. The Kb value for this is acetic acid times hydroxide divided by acetate. I can evaluate this against other expressions by multiplying by 1 in the form of H3O plus over H3O plus. So if I take this Kb value and multiply it by H3O plus over H3O plus, I can separate this in terms in the equation. Separating out on the top the OH minus, and separating in the H3O plus so that H3O plus is no longer divided over itself, I get the acetic acid on top, the acetate on bottom, times the hydronium on bottom, all of that times hydroxide on top, times hydronium on top, all over 1. Now remember that Ka is acetic acid times hydroxide on bottom with acetate on top, because we have the acetate, which is what it's forming, the acetic acid on bottom, and the OH minus on bottom, both reactants. Kw will be hydroxide times hydronium. If I substitute Ka and Kw in to the Kb expression, we find that the first half is the reciprocal of Ka, 1 over Ka. The second half is Kw. So overall, this process is Kw divided by Ka. Acetic acid has a Ka of 1.8 times 10 to the minus 5. The Kb then will be our kW of 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, or 5.6 times 10 to the minus 10. From kW and Ka, we can then find Kb. So rearranging the expression, kW is always equal to Ka times Kb, in the same way that kW is always equal to H3O plus concentration times hydroxide concentration. So if I want to calculate the concentration of a 0.1 molar solution of sodium cyanide, the Kb value is 2.5 times 10 to the minus 5. Sodium cyanide reacts to make cyanic acid and hydroxide. Initial concentration is 0.1, 0, and 0. Our change in equilibrium is minus x plus x plus x as before. So equilibrium concentration is 0.1 minus x, and then x and x. Plugging this into our equation, Kb is 2.5 times 10 to the minus 5 is equal to x squared divided by 0.1 minus x. Because 2.5 times 10 to the minus 5 is relatively small, we'll treat the Kb as being so small that we can ignore the x on the bottom, where 0.1 subtracts x. So we wind up with concentration of Cn minus on the bottom being 0.1. 2.5 times 10 to the minus 5 is equal to x squared divided by 0.1. This means that x comes out to 1.6 times 10 to the minus 3. That is only 1.6% of 0.1, so is a valid assumption. The pOH then is 2.8 because the negative log of 1.6 times 10 to the minus 3 is 2.8. The pH would be 11.2, which is 14 minus 2.8. And the percent hydrolysis will be 1.6. Now, Kb is analogous to Ka. We can use Kb to determine relative basicity the same way we use Ka to determine relative acidity. So just like an acid, a weak acid has a stronger conjugate base. A weak base will have a stronger conjugate acid. We can compare Kb for acid conjugates to evaluate their relative acidity. Something like Cn minus has a Kb of 7.5 times 10 to the minus 6. Acetic acid with acetate as its conjugate base has 1.6 times 10 to the minus 3 as a Kb. This is a much bigger value than 7.5 times 10 to the minus 6, which means acetate is more basic than cyanide. This makes sense since acetic acid is a weaker acid than cyanic acid is. Just like with Ka, we can evaluate in terms of a log scale, or a pKb. A high pKb is a weaker base, something like NO2 minus nitrite has a pKb of 10.7. A lower pKb is a stronger base, something like IO minus with 3.36 as a pKb. So the stronger the base, the weaker the acid. Something with a relatively weak base, pKb of 10.7, is going to be a stronger acid than something with a relatively strong base with a pKb of 3.36. High pKb values then equate to stronger acids, low pKb values to weaker acids. Now looking at salts of weak bases and strong acids, these salts are always acidic. The base reacts with water to form an hydroxide, forming excess hydronium. Something like ammonium chloride, reacting to form ammonium and chlorine. Water will have an autoionization process. The NH4 can react with the OH minus, consuming it faster than the H3O plus is consumed, yielding overall a higher concentration of H3O plus. Ammonium forms ammonia in solution. Overall, NH4 plus going to NH3. The Ka for this will be NH3 times H3O plus divided by NH4 plus. So finding the Kb, the Ka is equal to, or finding the Ka from the Kb, the Ka is equal to 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, since that's the Kb for ammonia. And we get 5.6 times 10 to the minus 10. Calculating concentrations of a 0.2 molar solution of ammonium nitrate, for example then, with a Ka of 5.6 times 10 to the minus 10, we have initial concentration of 0.2, change in equilibrium of negative x plus x plus x. Plugging this into our equilibrium expression, our Ka is 5.6 times 10 to the minus 10 equals x squared minus over 0.2 minus x. We can assume that 0.2 is negligible, treating NH4NO3 as approximately 0.2 molar. So solving for x, 5.6 times 10 to the minus 10 equals x squared over 0.2. x then equals 0.2 times 5.6 times 10 to the minus 10, and then take the square root of that, giving us an x value of 1.1 times 10 to the minus 5. Dividing that by 0.2 as a percentage gives us 5.3 times 10 to the minus 3%. Our hydronium concentration is then 1.1 times 10 to the minus 5, which is the same as our NH3 concentration. Our OH minus concentration is 1 times 10 to the minus 14 divided by the hydronium concentration, and our ammonium nitrate concentration stays at 0.2. The percent hydrolysis is 5.3 times 10 to the minus 3, pH of 4.96, and pOH of 9.04. Looking at the salt of a weak base and a weak acid, it depends upon the relative strength of the Kb versus the Ka. The conjugate base of an acid and the conjugate acid of a base will combine together to make these salts. So for instance, ammonium acetate. The basicity depends on whether Kb is bigger, less than, or equal to Ka. If a Kb is equal to Ka, the solution will be neutral. For instance, ammonium acetate. Both have a value of 5.6 times 10 to the minus 10. So ammonium forming hydroxide and ammonia, and acetate forming acetic acid and hydroxide form hydronium and hydroxide in the same amount. Overall, then, there is no net change in the relative amounts, so they both equal pH of 7. Kb is greater than Ka, however, will be a situation where we have the Kb being a larger value than the Ka. So for instance, something like ammonium cyanide. The Kb of cyanide is 2.5 times 10 to the minus 5. The Ka of ammonium is 5.6 times 10 to the minus 10. This is bigger than the ammonium is smaller than the cyanide, which means the base is bigger. So ammonium forming hydronium and cyanide forming hydroxide, the equilibrium for the first reaction is more towards the left than the second one is, which means that more hydroxide forms than does hydronium. In these situations then, since hydroxide forms at a greater amount than hydronium, the solution is basic. Now for a situation where the Kb is less than the Ka, something like ammonium fluoride, the Ka for fluoride is 7.2 times 10 to the minus 4. So its Kb value is 1.4 times 10 to the minus 11. This is smaller than the Ka value of ammonium at 5.6 times 10 to the minus 10. So the ammonium process producing hydronium and the fluoride process producing hydroxide, the equilibrium for the second reaction is more towards the left than for the first reaction, which means that the hydronium is produced in a greater extent than the hydroxide is. Since hydronium forms in greater amount than hydroxide, the solution is acidic. Now some salts of strong acids are acidic as well. If I have something like iron sulfate as a heptahydrate or aluminum sulfate as 18 waters, these each have small highly charged cations and a strong acid anion on them. In this case, both the anions are sulfate. These form complexes where 6 waters complex around the cation. The cation will draw electrons away from the water, causing the OH bond to weaken, making it more acidic. So for example, aluminum with a complex of 6 waters can react with water, forming a hydroxide and 5 waters in a complex and a hydronium produced. The Ka for this value is 1.2 times 10 to the minus 5, which is not bad in its acidity. The process occurs by the weakening of the OH bond. As the OH bond weakens, the H2O free water molecule can steal that H from the complex, producing a hydroxide in its place and a hydronium ion.